Grüezi ragazzi, bienvenue e willkommen to another one of Cannabis Ciencias LinkedIn Lives. I am quite excited about my guest today and what we're going to be speaking about. First of all, I hope everybody's having a lovely summer day. We are right now in our summer schedule, which means that we are only going live every 2 weeks for the months of July and August. So before we begin, big shout out to everybody that's tuned in right now. Thank you very much. And to everybody that's going to be checking out the recording at a later date, also, thank you very much to you. Please feel free to comment below, say hi, let us know where you're tuning in from. I know we have some people that RSVP'd from all across Europe, Latin America, North America. So we're always curious to know where you're tuning in from. Today's topic is the structural framework and therapeutic implications of endocannabinoid receptor signaling. Before we get into that, and before I pass the baton over to my guest to introduce himself, just a little bit of an intro about Cannabis Ciencia. Cannabis Ciencia aims to tackle the bottlenecks of the medical cannabis industry through the power of education. One of the services that we offer is our accredited education as a service. And on the screen right now, you actually see the kind of a bird's eye view of what these projects look like. And they start with the conceptualization, the definition and planning, development, organization, and marketing, and then, of course, the launch. Um, we also recently released our Principles of Clinical Cannabinology handbook. It is intended to be a complete resource for any healthcare professional looking to get started with medical cannabis. And if you have any more questions or would like to learn more about it, please feel free to scan the QR code. And then, just one last thought I'd like to leave you all with before we get started is that in Cannabis Ciencia, we are convinced that through education, we can increase adoption. With increased adoption, we can increase access. And through increased access, we can help more patients. So, apologies for the monologue. Enough with me. I'd like to pass the mic over to our guest for today. And first of all, Yassi, thank you very much for taking the time. And if you could maybe start by just giving us a little bit of an intro about yourself. Uh, I'm sure our audience, if they don't know you yet, are dying to know who you are.
Thank you so much, Villan. First of all, before introducing myself, I have to say very quickly that I'm a big fan of the work of Cannabis Ciencia and the education work you do. I am from Colombia, and a land historically stigmatized by a war against drugs. Cannabis, one of them, has been a big stigma for a long, long time in my country, and I have experienced firsthand that education is the only power strong enough to overcome these misconceptions. I'm very happy to share a little bit of the expertise I might have been able to gather across the years. So yeah, my name is Jesse. As I told you, I am from Colombia. I am head of drug design at Canafloss, a pharmaceutical cannabis company here in Germany, and I am a structural biologist. My job is to investigate the molecular structure of proteins, receptors, because understanding the structure, we can understand their function, and by understanding the function of proteins, we can think of um, um, therapeutic interventions or designing of molecular tools to actually address the diseases where these proteins might be involved. That's the job of a structural biologist, and also the job of a drug designer as I am as it has been my training. So yeah, many thanks for having me.
Amazing. Thank you very much. So, uh, look, I want to dive right into it because one of the things that I'm looking forward to the most about today's presentation is that we actually have some visual aids also today, which we don't always have in our LinkedIn Live. So, also to our audience today, we would love to know your feedback about what you're going to see on the screen today. And of course, don't forget to bombard us with your questions. We try to answer any question that we get throughout the process here, throughout the live. So, Yasid, I'm going to start with the first question right off the bat. What does the molecular structure of endocannabinoid receptors tell us about their function?
All right. So yeah, basically, the endocannabinoid receptors belong to a very known class of proteins, which are called G protein coupled receptors. Structurally speaking, they possess the typical seven transmembrane domains. So there's an alpha helicex. So you have to imagine this is the CB1 and the CB2 receptors overlap to each other. This transmembrane domain, as the name suggests, are crossing through the membrane. In the case of CB1, this will be the membrane of a presynaptic axon terminal. So how they work is that some ligands or some modulators of these receptors, like endocannabinoids or phytocannabinoids, might be, they will address the receptor in the extracellular matrix, extracellular loop. Then they will bind to a place called the orthosteric site, which is the main binding site of the receptor, although there are also allosteric sites that we will speak about in a minute. And this binding, what it generates is a downstream conformational change that modifies the structure of the receptor in the intracellular space. And if this molecular rearrangement is adequate, the receptor will assume something known as the ligand or the G protein binding competent conformation, and then we will have, through this molecular complementarity, we will have a downstream signaling process. So regarding the CB1 and the CB2 receptors, they are very similar to each other. So regarding the sequence, they are 44% identical, and the sequence is a similarity of 68%. So this means that they're very, very similar, CB1 and CB2. This is actually the reason why developing specific modulators for CB1 or CB2 is challenging. As we know, THC does not distinguish between CB1 and CB2. It activates both. And that there is an interest of the pharmaceutical industry for developing selective modulators for CB2, for example, because then they will have a non-psychoactive immunomodulator, and so to say. And it's very interesting because what characterizes these receptors is that they are actually behave like molecular microprocessors. So meaning like they have a lot of possible conformations, a lot of possible stages that can accommodate a lot of secondary messengers in the intracellular part to produce very, very distinct and very, very unique signaling pathways that result in the different functions that we know that these receptors fulfill. So, for example, when the right conditions happen, a kind of a G protein called GI that actually inhibits cyclic AMP signaling gets recruited, but when the situation is a little bit different, GS gets recruited, which actually stimulates. So inhibit and stimulation of a chemical pathway. These are opposite chemical pathways by the same receptor. So, and also in some conditions, very completely different secondary messengers can be recruited, also beta arrestins. So depending on what the endocannabinoid system or the body needs to keep the homeostasis and what ligands bind and what cofactors bind, we will obtain very, very different biological responses, which accounts for the biological diversity of the endocannabinoid signaling pathways. We know that CB2 binds to is able to like induce these pathways, CB1 a little bit more. Apparently, there is a little bit more of versatility of the CB1 signaling pathway, according to recent scientific consensus. But in the end of the day, we don't know anything. So, like the secrets of this endocannabinoid signaling, which conformation induces which biological response, is still a matter of research by laboratories of structural biology, like in the one I am. We know, for example, that we have like a very modest idea of how endocannabinoids interact with these receptors. So I want to make a quick recap. When there is, for example, something that breaks down homeostasis, as we know, endocannabinoids kick in to go back to equilibrium, because the endocannabinoid system is about equilibrium. So let's say we're stressed, and the endocannabinoid is able to mimic the molecular structure of the phytocannabinoid. That's why we are able to like expect similar biological responses of phytocannabinoids like THC. So in a normal situation, THC will, as anandamide will do, for example, an endocannabinoid, address the receptor. Imagine the receptor is a lock, and the ligand THC or the endocannabinoid is a key, it will open this lock, and then it will produce a biological response. But these as biological responses, as I explained you, are very diverse. In our conditions, we can have an effect in memory and cognition. We can have an effect in sleep, motivation, appetite, as we know we can do with medical cannabis, and also an effect in euphoria. But there is a fundamental difference between endocannabinoids and phytocannabinoids, and the difference is that endocannabinoids actually get regulated in our body. So there are enzymes that breaks them down, which once they have fulfilled their role, but phytocannabinoids do not. This means that if we take too much THC, for example, we will face these unwanted side effects that historically have been like the stigma behind the cannabis use. But in the end of the day, this is how like by mimicking the molecular structure of our biological key, which is the endocannabinoid THC, which comes from a plant, and by a evolutionary coincidence, we can somehow address this diversity of molecular processes mediated by the endocannabinoid receptor 1 activation. Yeah, it's more or less how the structure of these receptors relates to their structure, to its function.
Amazing. Thank you very much for that. And you just touched on some of the differences between the phytocannabinoids and the endocannabinoids, and they're structurally quite different. But how can they modulate the same receptors despite their differences?
Yeah, good question. Yeah, you're right. The keys are actually very different. So THC and andamide look structurally, they apparently are very different. And actually, to actually see how these two keys can open the same lock, we have to jump to an additional dimension. We have to go through a three-dimensional dimension. So let me just share you my other teaching tool, which is actually a molecular model, which will allow us to appreciate in three dimensions what I mean. So can
And
you see this right now?
one moment, you see, I'll just add it. Perfect. And just to the members of our audience watching right now, if you're tuning in live, if you're going to check it out later, definitely let us know what you think about this part of today's live. Are you a fan of this kind of 3D stuff? Because when I saw this, I was geeking pretty hard, to be honest. So Yasid, please continue.
Okay, thank you. And yeah, please, brace yourself. We are going into the molecular world, but don't worry, it's more intuitive as it seems. So what we have here is actually a 3D model of the CB1 receptor with the seven cross-membrane domains. So imagine that here is the membrane, here and here. This is the transmembrane space. Here will be the extracellular part, and here will be the intracellular part. And we are observing here is actually experimental data obtained through structural biology methods of THC binding to the orthosteric site of CB1. So this is the molecular basis of how THC can activate the CB1 receptor. So here we see that THC in green is basically an hydrophobic molecule. So it's basically carbon atoms. They don't like water. They like unpolar stuff. But that's exactly what the orthostatic site of CB1 is made of. You see, we have these residues here. They are called amino acids, and they have an important characteristic. These ones are like phenylalanine, tryptophan, leucine. They are hydrophobic amino acids. So it's like in chemistry, similars attract to each other. So hydrophobic likes hydrophobic. So what we see here is how the THC molecule nicely fits inside this lock that is the CB1 receptor. So if we look at how an endocannabinoid might bind, here I have a model of an andamide binding to the same orthosteric site. I have to mention this is not experimental data because this hasn't been like solved. This is a computational model that I developed using a technique called molecular docking. But the important thing here is that if we compare how THC binds and how the endocannabinoid binds, we can already see how they can open the same lock. You see, for example, this hydrophobic tail of THC, you see these carbons here, they occupy the same space as the lipidic tail of anandamide. You see here, they can address the same residues. They feel very comfortable in the same hydrophobic pocket. And you see that there is like a really cool overlap, you see, of how an anandamide actually bends within the orthosteric site and kind of adopts the molecular shape of THC. That's how despite these two molecules not being like similar structurally, when we go through the three-dimensional properties and when they they are able to overlap each other and address the same residues via a evolutionary coincidence between the plant and the mammal world. So yeah, this is basically how anandamide and THC can act in a similar ways, although they don't have a similar structure at all. Yeah.
Thank you. So I see already some comments about the 3D. I love it. I think that it's also great for our audience. The next question I actually wanted to ask you, Yasid, is how are endocannabinoid receptors actually activated and or deactivated in the body?
Sure. Let me just go back to my
Sure.
PowerPoint. So it's all about mechanistics. So as I mentioned you, there is a ligand that binds into the orthostatic site. Can you see my screen?
Yes.
Yeah, perfect. So yeah, as I see here, so it's all about structure. Structure determines function. When there is a ligand, here we have a model of the CB1 receptor bind to an antagonist or a molecule that blocks its activity. It's based on rimonabant. You might remember rimonabant because it was a marketed product. And here we have a model of the same receptor bound to THC or a derivative of THC that is an activator. So you want to see what activates and deactivates the receptors, and considering that structure determines function, we only have to compare the two structures. So here we have the overlap. We can see here in blue, we have the activated state of CB1, and in white, we have the unactivated state. So we see that there is like some movements here. You see, we compare alpha helix 1 or 2, like kind of open a little bit, and also in the intracellular part, the alpha helix 5 and 6. And if we go to the detail, as I will show you with the 3D model, we can actually pinpoint the whole activation mechanism to the movement of a few amino acids. With CB2, it's very similar. We also have experimental data on how it looks bound to an antagonist that you can see here. Also, we have it bound to a THC derivative, and then with the overlap, we can see that in the intracellular part of the receptor, there is a movement of alpha helixes 5 and 6. So how this and that there are very modest changes that determine what activates them or deactivate them. So I will show you like in a minute how this actually looks in the molecular world, because I think it's more intuitive in that way. I'll try to not to overwhelm you with that, but I think it should be fine. Just let me share this now for you.
I think it's probably quite difficult to overwhelm our audience. Our audience
That's great. That's great.
is on the
Good.
ball here.
I'm happy to hear that. So can you see again this model of the CB1 receptor? Excellent. So here we have our nice CB1 receptor, as I mentioned you at the beginning. Here we have it bound to THC. As I mentioned you already, it fits just perfectly to activate the receptor because it addresses the hydrophobic residues of CB1. And here we have an overlap with white with the unactivated states of the receptor. So to understand what determines that it's activated and unactivated, we just have to compare what is different. You see here these changes that I mentioned you in the outside and in the inside. Here we have a model, experimental data of how an antagonist of CB1 binds. Actually, this is, as I mentioned you, rimonabant. It's an elongated molecule, and you can see how it binds very nicely and deactivates the receptor. So now it's gonna get a little bit crowded, but just try to keep up. I will show you why this molecule deactivates CB1. So, and for that, we will compare it with the structure of the activated state, which you see right now in orange. So orange CB1 will be activated, white CB1 will be unactivated. You see that when the blue molecule binds, it cannot occupy the same space as these two residues called phenylalanines, 170 and 174, and kind of forces the whole thing to move outside. You see, this thing moves from here. And this is what forces the loop to open. You see what makes it move from here. And if we look even closer here, we observe that this chemical group that is basically present in all CB1 antagonists is the chlorophenyl. You know, we have two chlorides and one phenyl group. Actually, the halogen comes in the proximity of this very important residue called phenylalanine 200. You see, they come too close and it forces this phenylalanine to actually move from here to here. You see, it kind of forces an opening, like a flip of conformation. When this happens, in turn, this phenylalanine pushes this other residue, tryptophan 356, also a very important residue, a little bit up. And when this conformational change happens, actually what we observe is that what happens is a like butterfly effect thing, because these changes makes the whole receptor to modify its structure. You see, we have a moving of this alpha helix here. It moves from here to here, and then when this molecular movement happens, we actually take away the ability of CB1 to have molecular complementarity to the G protein. That's why just by modifying these two residues, you know, these are movements that are in the scale of a billion of a centimeter, they already deactivate the receptor. With CB2 is something similar. Here we have CB2 in an activated state. Here we have it bound to THC. I just want to show you very shortly how these residues will look in CB1. Here I am activated and deactivating the equivalent residues in CB1, and you see that they are like identical. This is the reason why it's so hard to achieve selectivity between CB1 and CB2, because the chemical environment around the activating site is very similar. But yeah, this was a small parenthesis. Here I'm making again the overlap with the unactivated form of CB2 in this case. Here we have this movement here, and then we look at the molecular detail. Here we have an antagonist of the CB1 receptor, or CB2 receptor, I'm so sorry. You can see here that if we compare with the activated form of CB2 that you see here in green, we just have to compare what is the difference, and then we know what makes it go active or inactive. And in this case, we see it's just this residue, basically, tryptophan 258, and a very modest change. You see here, this is like a change of around 60 degrees in the scale of a billionth of a centimeter, induced by this benzene group in the antagonist. You see, they cannot occupy the same space, so it gets pushed down 60 degrees. And this is, again, enough to make a butterfly effect chain reaction that changes the structure of the whole intracellular loop and destroys the molecular complementarity to the downstream signaling molecules like the G proteins. And that's how, with a tiny movement in the range of a billion of a centimeter, you can activate or deactivate these receptors, basically.
That's incredible, especially considering the scale we're discussing here. Just being a little conscious of time, there are a couple more questions that I wanted to ask you. One that I was really eager to ask you. We're speaking about phytocannabinoids, endocannabinoids, but what I also wanted to touch on are synthetic cannabinoids. And why is it that the synthetic cannabinoids are actually so dangerous? And perhaps that many people aren't aware about some of these dangers, in fact. Yes, you are on mute, by the way.
Oh, thank you so much. Yeah, excellent question. And I want to answer it by introducing you very shortly a new concept, which is the efficacy of cannabinoids. So remember, we are talking about the endocannabinoid system. Everything is about equilibrium. If we destroy the equilibrium, we go away from the therapeutic range. And in the molecular world, it's the same. Different ligands of the endocannabinoid receptor will induce a different level of activation or deactivation of the receptor. And this is called efficacy of cannabinoids. So for example, this is the activation diagram of the CB1 receptor. We have an antagonist, something that blocks the receptor, like rimonabant. We get this drug for obesity, but that got suspended because it caused psychiatric problems. So some people were making suicide. So this is like, imagine the receptor is a car, and we are with rimonabant, we are pushing the brake and actually going backwards, right? We are going in reverse. So this not okay. I mean, we get psychiatric problems. In the other side of the balance, if we go like full gas in the car, you know, we use accelerate, we get a full agonist of the CB1 receptor, and these are the prime example of the synthetic cannabinoids. We get agitation, anxiety, paranoia. They're very dangerous molecules. But it's just but by a coincidence of nature, we get a molecule like THC, which is actually a partial agonist. So it's a molecule that activates CB1, but only in a modest way. So we're not going full gas or full brakes. We're in the middle, in the sweet spot in between. We can develop like different molecules that are actually marketable and are actually useful for a disease, especially when combined with CBD. We get sativex and we have a safe drug for an indication. And it's the same lock. We're using different keys, right? We're using different keys. And yeah, do I have time to show you the model of how this works? Or
Sure, yes. Do we have another 4.5 minutes? There is at least one question that we should maybe address in the comments, but please feel free.
yeah, great. So I want to show you because I think this is very, very interesting why the synthetic cannabinoids are actually so dangerous and are so active. And we can explain it very easily, again, with this considering this structural biology facts. So as you see here, so this is the Fubinaca molecule. This is the one molecule that is one of the most dangerous synthetic cannabinoids. It's a component of spice. It has a really high affinity for the CB1 receptor, and is, as I told you, the molecule that makes like full gas, full accelerator in the CB1 receptor that causes, in very low doses, tachycardia, anxiety, and so on. If you have a heart issue, it can actually induce a heart attack. So what is interesting here is that when we compare it to THC, which is a partial agonist, we can see already why Fubinaca is way more potent. For example, here in green, when THC addresses the actor-steric site through this modest five-member carbon chain, we have this weak hydrophobic interaction. In the case of Fubinaca, we have an aromatic ring bound to an halogen. And actually what we get here is an interaction of the electron clouds of the two rings. So we have with the Fubinaca molecule and the tryptophan, this makes a really strong interaction. And also with the leucine. And if we look behind of the molecules, when THC has 2 carbons, you see, we give it an hydrophobic character by adding 2 carbons. Fubinaca has 3. So it feels even more comfortable in the orthostatic side, and it can bind more potently and have a stronger effects at lower doses. And finally, something that THC does not have, Fubinaca have this a carbonyl group. So it's basically an oxygen. Oxygen has a partial negative charge. The partial negative charge likes to interact with a positive charge, which is the nitrogen in the histidine 178. And this kind of a magnetic interaction is called hydrogen bridge, also gives it an additional affinity. That's why this molecule in very low doses can really activate CB1 too much, bring us away from the safe activation range of CB1 and pose a public health issue. Yeah.
Very, very interesting. And I want to, as we are going into the last 2 minutes, actually, we have, let's see here, Miss Viola Brugnatelli asking a question. First of all, thanks for sharing your knowledge, Dr. Yasid. And the question: does it exist experimentally a chimera CB1, CB2 for basic research?
A chimera. Good question. I think I saw in one really interesting paper. Yeah, I remember now. So there is one really interesting paper. I can share it with you, Viola. By the way, I really admire your work, and I'm happy that you're asking me a question. Yeah, and there is one really cool paper where they compare the structure of CB1 and CB2, and in an intracellular loop, they mutate CB2 in a way that it resembles CB1, and by doing so, CB2 acquired the ability to address the secondary messengers that CB1 can. So yeah, there are some research like they try to experiment with this, and you can see how you can actually engineer CB1, CB2 to look more alike to each other. And if you are interested in that from the research perspective, you can get it done through site-directed mutagenesis. Yeah.
So, on that note, thank you very much to Viola Brugnatelli for the question, and thank you, Viola, for making all of this possible. Big shout out to you. And yeah, you see, there was actually one more question that we were hoping to get to, which we've run out of time now. But the question was, what are some applications of understanding the molecular structures of endocannabinoid receptors? Perhaps this is something that we could add in the comments for our audience. But I'd like to take this opportunity to personally thank you, because it was a big treat for me to be able to be here with you today, and have the front row seat to your presentation. Also, again, big thank you to everybody that tuned in our audience. Please let us know what you thought. Let us know what you thought about the visual aids that we incorporated this time. If you'd like to see more of this type of material, especially the 3D models, let us know. Thank you to everybody tuning in from all around the world. I saw Spain, Germany, the US, Canada. So it's Nigeria too. Shout out to Daniel. And yes, big thank you to everybody. Yes, thank you to you also for your time. And on that note, I hope that we will see each other again very, very soon here, and to discuss some more cannabinoid science, and geek out on some more 3D models. Thank you very much. And thank you to
You're
everybody.
welcome. Thank you for having me. It was a pleasure, and see you next time.
Thank you. Take care, everybody. Ciao.